Okay, so this is lecture 2, video 3, and we will build on our simple perceptron hypotheses, and we'll try to come up with an algorithm so that we can pick appropriate weights that will decide our final G. And just a reminder, G is nothing but our final hypotheses. Okay, so let's move forward. And in order to understand this algorithm, I'm getting into the geometry of the perceptron. So basically, I'm trying to look at how, like, the pictorial representation of how a perceptron looks like. And what we are going to do is we are going to look at a two-dimensional representation because it's easier to view that, right? Two-dimensional is nothing but a line. So in two-dimensional space, right? In 2D space, my W transpose X is a line, and in any d-dimensional space, this W transpose X would be a hyperplane, right? So this is something that is known to us, right? Basically, this W transpose X equals 0 is the equation of a line, right? And what we're trying to understand is how this plays into this entire data space, right? So let us assume that we're looking at only two components of W, that is W1 and W2. And of course, you have the W0 that we derived in the previous video. And then the X's have the augmented value 1 and then X1 and X2. So this X1 and X2, let's assume one of them, and I'm going to show you a better picture in the next slide, but just to like make things clear here, is let's say income and age. So this is my X1 and this is my X2, right? And my weights are the values that are assigned, right? The weights of each of these. So essentially, if I have, let's say, let me close this. Let's say my W transpose X is something like this, right? The normal to this is nothing but the components W1 and W2. So that's how this line comes into picture. And the W0 is essentially, if you remember the equation of a line, W0 is going to decide where exactly this would cut the axis. So basically the position, right? W0 decides the position, and W1 and W2 essentially decide the orientation, like whether it should be oriented like this or like this or like this. So slope, basically, right? So W1 and W2 are going to decide that. So based on this, this is how this picture in a 2D space looks like, right? Okay, so our goal here is to pick one of these lines, right? And that's why we are trying to understand the structure in a two-dimensional space. Let me show you a better picture so that we understand this better. So this is what this looks like, and just a reminder, my hypothesis set is nothing but sine W transpose X, and we are looking at it in a two-dimensional space. So this is, I think, age, and this is income, right? And this is the normal. And so again, as you can see, I can have like multiple lines, right, that satisfy this expression here. Like this is a valid one, this is a valid one, right, and so on, because like our final goal is to pick an appropriate WT and essentially W, right, the elements of W. So which one should we pick, and based on what should we decide that this one needs to be picked, right? So that's the big question, which one to pick, because this could be like one perceptron. Let's say I'm calling it P1, this could be P2, and so on, right? So it's my goal is to pick the best one. But how do I decide which one is the best one? Okay, so having said that, I know that I have this training data. I know that I have some data that I can use to pick that perfect line, right? My goal in this case, in income and age, if you remember, our income and age are nothing but the features for the credit card approval problem. And my goal was to say a yes or a no, right? And so one answer to our question, which one to pick, could be to look at them given my data, right? So in this one, as you can see, let's say this is my perceptron or my H1, right? And you can see that these blue ones represent, let's say, the ones in which I said yes, and the crosses are the ones in which we said no, right? And this divides the space, my hypothesis divides this space of yes and no, right? So if you look at this one here, right, we have these misclassified points. Basically, these points are on the wrong side of my hyperplane or my line, let's call it a line, right? For H1, let's say I'm calling this one H2, right? And as you can see, there are no misclassified points. All the blue ones are in the blue space, all the red ones are in the red space. So this perfectly divides my yes and no space as I would like, right? At least based on the data that I have. So, like if I have to choose in between these two, obviously I'm going to pick this one because this looks like really good. But now there are a couple of questions we need to answer. First of all, how did I like come up with this versus this, right? And is there something like, of course, deciding which one is better is like we can compare each one of them. But if you think about my h of x, this has like an infinite number of possibilities, right? So even after looking at these two examples, it is not completely clear to me which one I should be picking up. So basically the questions that arise are if I have to learn a final hypothesis G, right? Because here in this case I decided, okay, this is good, so my G is essentially my H2. So this is my G, right? But now in order to get that final hypothesis G from H, we have to understand what do we want, right? So basically we want to decide like which hypothesis out of my H of X is better, right? So that's what we want. What does that mean in terms of the data? Well, in terms of the data, if I have some training data, I want to see which of the functions that I'm going to finally pick up looks better in terms of data. So which one looks better? For example, in a previous example, my H2 was better, right? So I picked that up. Now the big question that we were like a little bit confused about earlier as well, how do we find this better H? Because I know that my H of X has this infinite possibilities of all W's, right? So basically I can have this like W transpose X with almost any W here, right? That satisfies this equation because like it's like everything. So we need to come up with some criteria to pick, which is what my learning algorithm, which is also known as the Perceptron learning algorithm, is going to do, right? So we have to come up with some criteria to pick, and that criteria should pick a hypothesis that looks better on my given data and then implement that criteria, right? So let's see how we can do that. And another question that arises like right after this is how should we get started? What is the starting point? Well, all of those questions will be answered now because now we are going to look at something that's known as the perceptron learning algorithm. So let's see what this perceptron learning algorithm does, right? Essentially, we are trying to find out a hyperplane, right, or a line in a two-dimensional space that perfectly separates these two regions of yes and no, right? This is what my like idea is. Okay, so the way we get started is that we want some point in my data, in my space, that I want to get started with. So for example, like the high level idea of the perceptron learning algorithm, let me see if I have a picture. High level idea is, let me draw that picture again in which we had like the points separated, right? The ones that had like the wrong points on the wrong side. So let's say this is my blue side, right? And I have like these 4 points, right? And these are like my misclassified. Um, yeah. So this is not my misclassified. These are the correct ones. Let me see if I can get rid of this. Yeah. Sorry. So this was like the correct one, right? Yeah, this because this is my red side. So yeah. So I have like this misclassified point here, and these two are because like the crosses are for the red one and the circles are for the blue one. Okay, so this is the red side, this is the blue side. Now I know that this one is misclassified, right? And can I do something to my hyperplane, which is let's say this h1 or my line, right? Such that whenever I find this misclassified point, any one of those, right, I can move my line in this direction so that it gets here, right? So basically what I'm trying to do is like this line would be somehow become like this, and this would be in the correct side. So one misclassified point will go into a like the correctly classified region, right? So this is the fundamental idea behind the perceptron learning algorithm. What we do is we start with some weight vector and keep trying to improve it based on the misclassified points that we have, right? It sounds really simple. It is actually as simple as you might think. But yeah, there can be some drawbacks that we'll discuss right after we have understood how this works, right? So basically what we are doing is we are picking a random hypothesis. Let me write it down. Pick any random, and then there are ways to do that better, right? Any weight vector. And this 0 represents, because we'll have iterations in this algorithm, so basically this W is going to be WT. T is the iteration number. So let's say this is my first iteration, right? Nothing has happened. So let me pick some weights. Maybe I can have like the weight vector something like this, like 0, 0 and 0. That's also fine, right? Any values. That's what I'm saying. Basically pick any values, have any values for my W, right? And just like plot this, for example, here, right? Now, if this does not look good, and how do we know that it does not look good? Because we'll see there are misclassified points, right? And of course, this would be extremely rare that my very first hypothesis really, classifies my data correctly. This wouldn't be the case, right? So what you'll do is you're going to pick one of the misclassified points, just like we did here, right? And then move the hypothesis. So that means move my W transpose X, which is my line, in the direction where we can improve on that one bad point, right? Now the question arises, how can we do that? First of all, so how will we do that? Which I'm going to show you just now. And of course, you might think that we may misclassify other points, right? So for example, if I had something like this, right? And I moved this one like this, just to include this one point, like in this example here, right? And maybe there was this like correctly classified point somewhere here that starts to fall here now, right? So that like we can like mess up other points depending on what kind of data we have. And so there are certain assumptions on which this algorithm is built, but let me show you why this is the case, that this classifies it correctly, right? Okay, so let's say let the misclassified point be X star, right? So I'm just like calling that one point X star, right? And my W is the W0, right? I'll have like something that I just picked randomly, right? Now, because this point is misclassified, right? Which means the sign of the dot product of my W0 dot X star, let's say, is 0 or is greater than 0, which means that like if this is the case, right? Because if you remember, these are my +1 and -1 regions. That's what I'm calling them, because this is a classification problem, just so that we are clear on this, right? So which kind of tells me that because this was misclassified, sorry, not qualified, this is misclassified. So let's say the sign of this is greater than 0, then it's clear that my Y star, so Y star, I'm calling the Y outcome of that particular point. Okay, quickly give you a review of that. If my misclassified point here is called X star, so this is my input, then the given label or the given outcome, which we've been calling for this, right? Because this data is given to me, I have the answers to all the questions. So my Y star would be the outcome that's given for this one, right? So basically, I have this misclassified point where I picked some W, which is nothing but my line equation, right? And did a dot product on that X star, right? And if I find that this is greater than 0, then obviously this must be less than 0. And that's why this was misclassified, right? So if you look at the vector sort of pictorial representation of this, if this is my X star, right? And if this is my W0, right? Which means this angle must be less than 90, right? Which is why I'm getting this. But actually, I should have had like something in between them that's greater than 90 to get the same Y star as is the outcome given in the data, right? So what we can do is, as of now, what we can do is we can move this vector in a direction opposite to what it is, so that we can have that kind of an arrangement. And what do we do to get that? what we do is we simply add another vector that's exactly this x star, but multiply it by the opposite sign. And how do I get the opposite? How do I ensure that I multiply it by the opposite sign? One easy way would be to simply multiply it by y star, because it already has that opposite sign, right? So if I add this to this vector, I will get this outcome as my wt, which I'm like calling it more generic now, right? So basically, if this was w0, this is going to be w1, right? Similarly, if there is a misclassified point that has sign like the dot product of w0 and x star, let's say, is less than 0, then because this is misclassified, it tells us that my y star must be 0, right? So now in this situation, basically the angle between x star, because this is the dot product thing, right? So basically the angle between this and my w0 must have been greater than 90, right? And what I need to do is make it less than 90, right? And so for that, what I need to do is add a vector, right, in a direction opposite to this, right, such that I can take it until like less than 90. So basically what I'm doing here is simply multiplying it by y star x star. And I'll get this vector, which will be w1 now, right? Because this was w0, so the next iteration is w1. This is how iterations in a perceptron learning algorithm work. And so eventually I'm going to get the correct vector, and this misclassified point will be classified because I actually moved my line. I moved my w, right, in the right direction. So basically this update rule, which does this, w1 is w0 plus y star, the misclassified point with the outcome, which was my y, because this y is a plus and a minus, right? So basically this is my update rule. And once I'm done with that update, if I see more misclassified points, I am going to repeat this over and over, right? This is repeated and until I keep improving. So we will have like a whole discussion on when to stop, of course, but right now this is important to understand why and how we are improving, right? So we are improving based on this update rule, right? This thing here, this is the update rule, and we keep going until we can improve. Okay, so let me kind of summarize everything that we said here. So this is the PLA, or the perceptron learning algorithm. We begin with anything. So here, instead of w0, we are beginning with w1. Let me call that like all the values are 0, right? For all these iterations, we find the weight vector wt from the data. Pick any misclassified example, as I said. Call that example. Of course, for that example, this would never be equal to the sign of the w, which is my line, times the misclassified point, will never be equal to the actual outcome given. That's why it's misclassified, right? So what I have to do is I have to go and update for that particular point and keep doing that, like keep repeating that until we'll see when to stop. So there are stopping criteria. You can definitely point this out here, that this seems to be an infinite sort of loop, which is true in certain situations, right? So a lot of things can go wrong actually. So the criteria that we are basing our entire algorithm can be bad. If we are improving one point, as we saw, we might mess up the other point. If data is not linearly separable, this can go into an infinite loop. So the big assumption in PLA is that the data is linearly separable, right? If it's not, then there can be this infinite loop going on. But there are ways to handle that, as we shall see in, I think, lecture 3, when we talk about the pocket algorithm and other things. So I'm not going into that. It's important for you to understand what PLA is and how it works. And there is a theorem that we're going to talk about in a short while that shows us that this PLA converges if the data is linearly separable. Okay, so I'll see you in the next video. We will begin talking about the convergence of PLA, and then we'll look at other learning paradigms. Okay, thank you.